again, in our last video we took a look at two-dimensional arrays, and a two-dimensional array was a way to represent a grid sort of shape, such as you might use if you were making your own, say, chess game or Minesweeper game, or pretty much any scenario. Like, for example, you wanted to represent matrices in math class, you might use a two-dimensional array. So two-dimensional arrays are actually infinitely useful data structures. We looked at the syntax for making one of these two-dimensional arrays, and that looked like this. We have two sets of brackets when we declare the type, and the reason we have those two sets of brackets is that this variable g that referred to my two-dimensional array is really an array of arrays of integers, an array of arrays. And here's the line of code that actually makes the array, and here's a line of code that actually starts assigning to that array. And we know that under the covers, g is really an array of arrays, so it looks something like this, where g refers to this pink array, which itself contains these yellow arrays of integers in blue. And so when I write g2, I'm referring to this array. And when I say g23, I'm referring to this box. And then in this code here, I assign the number 3 to that box. And here I decide to print that number. And we also learned that if you want to know how many rows are in your array, you ask for the length of your array. If we assume that the first integer refers to the row number and the second integer refers to the column number, then we can get the number of rows by using dot length, because the number of rows is the number of subarrays. The number of columns is the length of any one of those arrays, so array 0 is as good as any of those arrays, so we can say g0, that's this array, ask it for its length, we get 4, and that corresponds to the number of columns in my grid. Right now, I want to start solving some problems that use this idea, so let's draw a nice big purple line across so we can separate the old from the new. And the problem I want to solve is, let's just figure out, is a particular coordinate valid? Is a particular set of coordinates valid? So public, so anyone can call it. Static, so I can call it directly on a file name. I don't think this is too important though. Boolean, because it's going to return a true or false that tells me whether or not a particular row and column are valid for a particular two-dimensional array. And I'll stick with a two-dimensional array of integers, and I'll keep calling it g to be consistent here. So that's the problem. I want to know if this row number and this column number, which I tend to usually call col because it will look symmetric with row being 3 letters, if this row and column number corresponds to a legitimate row and column number on G. So what would be an invalid row number? Well, an invalid row number would be something like, for example, -3. I can't have coordinate -3. Actually, maybe let's look at my example first and make sure we understand what valid row and column means. So on this particular grid, actually let's look at this picture. On this grid, a row number of 0, 1, or 2 is valid, but anything less than 0 or greater than 2 is invalid. And here a column number of 0, 1, 2, or 3 is valid, but anything less than 0 or greater than 3 would be off my grid and therefore invalid. So that's the problem I'm trying to solve. And I find a lot of two-dimensional array problems, I end up finding this little method to be useful to me. So, first question is, it's valid if the row number is, actually let's deal with invalid maybe. If the row number is less than 0, that's no good, right? That would be invalid. And so we could return false in that case. If the column number is less than 0, that would be false. How about if the row number is too high? So how many rows do I have in my grid? Well, I remember the number of rows is, in fact, maybe we should take this off the screen so we actually have to think for ourselves. The number of rows is g.length. And that's the number of rows, so the last row has index g-length minus 1. So if I'm greater than g-length minus 1, I've gone too far. So return false. And likewise, if the column is greater than, well, let's see, what's the last column? How many columns do I have? Well, any particular row, if I ask for the length of that row, gets me gets me the number of columns, and so the last column is that minus 1, and in that case I would return false also, and otherwise I can return true. If none of these bad conditions were met, then it must be a valid set of coordinates, so we can return true. I just want to write that real quick another way. one elegant way is we could write this all in one line. The coordinates are valid if when the row number is at least 0 and less than the number of rows, and the column number is at least 0 and less than the number of columns. So maybe you prefer writing it this nice shorthand way here. And I think it's important to be able to challenge yourself to use what you know about Booleans to sort of simplify these situations where you have lots of ifs. Lots of ifs often means you can use ands and ors to simplify your work, and whenever you find yourself writing, well, let's just leave it there. I think we'll explore Booleans in other videos, and you've probably seen those videos by now. So, is valid. Let's write another one. Let's determine the sum, let's determine the, sum around. Int sum around. So sum around is going to take in the same arguments. Some two-dimensional array I'm calling G, and a row and a column, and it's going to return the sum of the values around that point. So, around that coordinate. So if we pass, let me go back to this picture. If we pass row 1, column 2, which is right here, then finding the sum around, we'll say the sum around means looking at this cell, this cell, this cell, and this cell. And so in this case, the sum around that is 0. 0 plus 0 plus 0 plus 0. Let's take one more example. Suppose we ask the sum around this one. Now it should be 3, because there's 0 plus 0 plus 3 plus, and we'll make sure not to count this invalid one. And we'll make sure we don't crash either. So that sum around this cell would be 0. Sorry, would be 3. 0 plus 0 plus 3 is 3. Okay, so that's the challenge, sum around. And that might be useful to me. I don't know what problem I'm solving here, but I suspect I would use this kind of idea in many situations. For example, if I'm writing Minesweeper, I might want to know how many mines are around a particular location, and it might be a similar block of code. So how do we find the sum around those particular coordinates? Well, first we want to know, how do we find, so G row column is the value at that particular row and column. How do we find the value just above it? Well, the value just above it we can get to by decreasing the row number. One less row. Right? So if we're here, the value above that spot is the value in row 1, column 2. So one less, decrement the row, or one lower row, and the same column. So row minus 1, column. But that might be off the grid, right? So we might need to check and make sure that's on the grid. One nice way we could do that is we could write a little helper method that we'll call it value in. And value in is going to do pretty much just ask what value is in that row and column, except for one thing. If it's invalid, so returns, well, I think it'll be obvious when we look at the code what it does. If it's valid, if it's a valid location, then we'll just return the value there, and otherwise we'll return 0. And that's going to be very useful, because now if we want to know the sum around, well, that's the value in, actually means I don't need all of this. Here we go. The value in G row minus 1 col, that's the value above. We're going to return that value plus the value in, let's see if we can get the indenting right here. Oh, forget it. We'll make the indenting wrong. The value in, let's see, to the left, that would be the same row, but one lower column, plus the value in same row, but I want, sorry, this is to the, maybe we should use some comments, make this pretty. So this is the, here, I'm going to write it like this. This is above, plus this one is to the left, plus we want to the right. To the right would be the same row, but the column would increase, and below would be the row plus one greater row, but the same column would be right below. Oops, my semicolon better be before my comment. And there we go. That's the sum around that particular cell. And so we'll often, I think, in two-dimensional arrays, want to find not just what value appears before or after, like I might in a one-dimensional array, but what values appear above, below, left, right, maybe diagonal from me, and all sorts of things like that. Alright, in the next video, we'll try a couple more involved methods. Maybe we'll take a look at some two-dimensional array methods that require loops. I'll see you in that video.